Good evening. Good evening, everyone. Thank you very much for coming to the second talk of the term. Tonight we welcome Professor Sir Michael Berry of the University of Bristol. In 1982, he was elected Fellow of the Royal Society. In 1990, he won the Gold Medal of the Society, and in 1986, he was knighted. 2 years later, he won the Wolf Prize in Physics, and in 2000, he was jointly awarded the Ig Nobel Prize for levitating a frog. We are extremely proud of having him tonight. Please welcome Professor Michael Berry.
Well, I'm delighted to be here. It's not the first, it's the second time I've spoken at CUPS, and I understand that you didn't use this lecture theatre till recently, but I think long ago when I came you did. I have some vague memory of pharmacology. Anyway, it's a pleasure, and the title of my talk, the somewhat enigmatic title, is How Quantum Physics Democratized Music. Forgive the gloom. I had hoped that you could have some lights on at the back, but the ones that remained on were the ones which would sabotage the talk, so you can sleep comfortably. Now, the underlying theme of this talk is connections. In its generality, it's very familiar, but it's less so, I think you'll find, when we dig into details. Now, it's a cliche, this only connect, this famous quote from E.M. Forster. It's part of a longer paragraph, not to do with physics, live in fragments no longer. Now, the same advice has been given many, many times. In his retirement speech, my colleague Sir Charles Frank said, physics is not just concerning the nature of things, but concerning the interconnectedness of all the natures of things. And that's a very, very wise comment. Now, my connections will be some that link physics not only with other physics, but also with matters outside physics. Now, over the years, I've accumulated a number of bees in my bonnet, and I'm going to use this occasion to release a few of them, but there's, I hope, stingless bees. Good. So let's start with the example in the title, I'll dispose of, and that will set the theme. This is a compact disc player, invented in 1982. It's a 4-mile spiral of music, encoded as bumps and pits. Music is encoded from the inside outwards, and it has dimensions, microns in one dimension, nanometers outwards. And here's about 1,000th of a second worth of music. It's sampled at roughly 1/44,000th of a second, and that's a bit of about 1,000 hertz sound, and that's a few octaves above middle C. Now, at the heart of this device is a laser. There it is, at the heart of the device, and you know what happens. The laser was invented in 1958, and it scans the surface and reflects the bumps and pits as the disc turns, and it actually slows down from the start to the finish to keep the reception constant. And then the signal is bright, dark, on and off, is converted into electricity and then back to sound. Now, underlying the laser itself is a central principle of physics, which was discovered by Einstein in 1917, during the 2 decades of bewilderment that eventually led to full understanding of quantum physics. It was about 10 years later. Now, there were puzzling experiments concerning matter and light. And Einstein was thinking about how the two are related. Now, he knew, and you as students know from Niels Bohr, that in microscopic objects, the states are quantized. They can have only discrete values of energy, and that's something which was outside the previous Newtonian physics that works so well on our human scales. We celebrated last year the centenary of Bohr's discovery of energy levels in atoms. Now, Einstein knew, although it was a heterodox idea at the time, that not only matter but also light has a granularity, and later, of course, they were called photons. And that was mysterious in the older physics, because then there was the discordance with electromagnetism. Now, what came to him in 1917 was an insight while groping towards the full quantum theory, and the insight, which still seemed miraculous, was that these ideas about light and matter could only be consistent, compatible, if there were three processes by which atoms could absorb and emit light. Well, an atom can absorb light that shines on it, and it can be excited from one energy level to a higher one. No surprise there. Once excited, the atom could emit light by spontaneously and randomly decaying back to its lower level. Now, Einstein recognized the need for randomness. Eventually, that was incorporated into the full quantum physics at a fundamental level by Max Born, but Einstein didn't like it. And already in 1917, he wrote, "The weakness of the theory lies in the fact that it leaves the duration and direction of the elementary process to chance according to the present state of the theory." We're now in 2014, it's still true. Random. Now, that spontaneous emission was the second process, but the true originality from Einstein was to argue with some causality and reciprocity arguments that I won't go into, that you need a third process. And the third process was stimulated emission. An atom also emits light in a way that depends on how much light shines on it already. It can absorb light according to how much light shines on it, also emits light. And that stimulated emission was a new process that eventually led to the laser. And you all know, I think you probably know, stimulated emission. You've got light and you've got an electron coming along in an excited energy level. Here's a photon coming along, and it stimulates this atom to this electron to go to a lower level. Sorry, I'm talking nonsense. Here's an electron at a higher excited energy level, and it produces two photons at the same wavelength and phase. And this process continues if you keep pumping the by an external process, pumping the electrons up to the higher level. You keep stimulating more and more photons, but they're perfectly coherent, and in the end you get this pure bright light coming out. Now, here's the point that I'm emphasizing, that I'm leading up to. It was unimaginable in 1917 for Einstein that his quantum physics ideas would lead to the invention of the laser, this pure bright light. That was just a few years after he died, 1958. Now, in turn, it was unimaginable in 1958 to those physicists, experimental physicists of a different kind of cleverness to Einstein, that in 1982, engineers with another different kind of cleverness would use the laser in a compact disc player. I remember when I was a student, lasers were new. And they were very mysterious, beautiful things, and they were described as an invention looking for an application. Nobody had any idea what lasers were, because you have them in the supermarkets now, as you know, but I'm speaking about the laser. Now, not only physics was involved in this unanticipated connectedness. You know, you need engineering, of course you do. You have to make the thing work. You need mathematics, very subtle mathematics, to code the sounds into the bumps and pits in a way that gives you robustness against dust and scratches on the compact disc. You need business, you need finance, you need advertising, and of course you need music. That's what you want to reproduce. So, fundamentally, a compact disc player is a quantum physics machine. Now, with a CD player, it was the first time, conveniently, that humans could hear music anywhere in the world. You know, on mountains, it could be in the desert, it could be on the sea. This was a new thing, available to everybody, essentially perfectly reproduced. So you really can say that quantum physics has democratized music. So that's my title, my first point that I want to make. Now, I'm very much aware that every invention has a complicated history. The CD player was one stage in a long process. Before the CD player was the gramophone. Now, you could hear music in your homes with the gramophone, but you couldn't sort of carry it around very, very easily. I can't resist mentioning this chap, Emil Berliner, because he was a pioneer of the first commercially successful gramophone. Now, my mother's unmarried name was Berliner, and I have a cousin who would like to believe that he is somehow related to us, but I don't see any evidence for it, apart from the name. I would like it to be true, but I don't think it is. Now, gramophone, of course, wasn't portable. Then came the radio. That was a huge advance, but you couldn't choose what music to hear. Then some of you may just remember the Walkman tape player. Well, tape is less convenient than a disc, because you have to. It's not easy to actually go to the part of the tape that you want. So the CD player was the first convenient thing. It's itself been superseded, of course, by MP3s, iPhones, and the like. They're more convenient still, but they're also quantum machines, because they're based on transistors inside, and they're designed explicitly using the quantum physics of a class of materials, semiconductors. And I chose the CD player simply to illustrate the point about connectedness. Now, one of the bees in my bonnet is a very strong dislike of the term real world. I don't know how often you've heard it. It's usually employed disparagingly. It's the world that we don't live in, contrasting the abstractions studied in academia with the real world of, usually it's money that these people are talking about. It's very strange that anybody should think that money is more real than electrons and atoms and stars and planets, but they do. Ask yourself, or ask those people, next time somebody says, well, I'm in the real world, in your bank account, where exactly is the money? Well, it's an abstraction. It's the essential part of being human, actually, to invent abstractions and regard them as existing independently of us. Abstractions are useful tools, the ones in physics as well, helping us to navigate in an ultimately unknowable and infinitely rich world between different levels. So the only difference between abstractions that they talk about and ours is that ours are less familiar to them, that's all. But of course there is economic value in physics, and it extends vastly beyond my little CD player example. I read that the high-energy experimental physicist Leon Lederman, a Nobel Prize winner, estimated that 25% of the gross national product of the industrialized world depended directly on quantum mechanics. Other reports said 30%, other reports said 1/3. I wanted to track down this estimate, and eventually I found an interview with him. He got quite a sense of humour. This is Leon Lederman. He said, according to some absolutely closer to truth testimony I gave before Congress, quantum mechanics accounts for 37.9% of the gross national product, or some number like that. And the interviewer said, how did you get that percentage? And Lederman said, well, I made up the number, but it's plausible. You get it, I'm quoting him still, by tallying up what we have thanks to our understanding of quantum theory. Without that understanding, we would not have had transistors, therefore microprocessors. The whole microelectronics revolution wouldn't have taken place. Our computers wouldn't be what they are. The biotechnology revolution was catalyzed by Watson and Crick's discovery of DNA in structure in 1953, which was stimulated by a book by Schrödinger on the quantum theory of large molecules, What is Life? The core, I'm still quoting, the core products of 21st century technology, electronics, computers, biotech, all relate directly to an understanding of quantum theory. Now that quotation doesn't even mention lasers. You know, I said scanning our purchases in every supermarket checkout. Elsewhere, Lederman mentions MRI scans, magnetic resonance imaging based on quantum mechanics of nuclear spins. $5 billion a year. It's a pity that the N has been deleted from NMR. If you go to a hospital and you have a magnetic resonance imaging and you say nuclear magnetic resonance, the technicians who operate the don't know what you're talking about because they're forbidden to use the word nuclear. They've forgotten about it now. PET scans, positron emission tomography, based on annihilation of particles and antiparticles, linking quantum physics and relativity. Particle accelerators, treating cancer, plastics, diagnostic radiography, 25 billion. And I don't know what that adds up to, says Leon Lederman, but it's a lot. Good. Anyway, back to democratization. Here's another example of democratization. In October 1833, a young English gentleman, Henry Fox Talbot, on his honeymoon, which is what rich English people did on those days, sat sketching by the shore of Lake Como in Italy. That's what these young rich kids, gentlemen, did. They went on these longer holidays with their new wives and pretended they were artists. And he had, one eye was pressed to a camera lucida. Now that's a draftsman's aid, and with which you use it to superimpose a distant scene on some paper that you can then draw around, and it helps. You can trace around it, and here we are, so somebody doing that. Now, Talbot saw on the page of his sketchbook an image of the Italian landscape, and it seemed very easy to trace the features of the building, the village, and the lake, and the mountains, and so on. But it only seemed simple. He was actually crap at it. He discovered later he was useless. He quoted this: "But when the eye was removed from the prism, in which all looked beautiful, I found that the faithless pencil had only left traces on the paper melancholy to behold." So here's his rubbish sketch. And when he then recalled, I'm quoting him, the inimitable beauty of the pictures of nature's painting that the glass lens of the camera throws on the paper in its focus, that's almost the same place, then he thought how charming it would be if it were possible to cause these natural images to imprint themselves durably and remain fixed upon the paper. And he experimented for several years, and he invented the type of photography that we all used for more than a century. The invention of photography is a complicated story. It involves a number of people, and also chemistry as well as optics. It involves common salt, silver nitrate, sodium hyposulfite, Wedgwood, Niepce, Daguerre, very famous for it, Herschel, and then Talbot. What Talbot did different from all the other people, it was a seminal contribution, is that he invented the negative. Now the beauty of the negative, I mean, this is the famous first picture of a window in the house where he lived, Laycock Abbey. He was a very wealthy man, and that's the window now. The point about his negative-positive process was that with one negative, you could then print lots of copies, and this could enable people who could never travel to places or to see landscapes and works of art. In other words, it democratized the image. That's what he did. With the other people, they invented, especially in the case of Daguerre, extremely beautiful pictures, but they were one at a time works of art. You couldn't reproduce them. Well, that was photography until the 1990s. It was democratic, but it was imperfectly democratic because it employed plastic films, photographic film. They had to be sent to specialist technologies. You had to take your picture to be developed. It was fascinating, if you ever, how many of you have ever done this, to see the picture developed, being revealed. In Portuguese, the word for developing is revelação, revealed. You still see in Brazil faded shops, which used to be photographed developed with revelação written on them. Well, then, of course, came digital, which we all use now. And that completes the democratization by giving individuals, us, complete control. And so instead of film, the image falls onto a CCD, a charge-coupled device. Well, that captures the light by the photoelectric effect. Precisely the quantum process identified by Einstein in 1905 in the seminal first paper that he wrote on the granularity of light. So the digital camera is another quantum physics machine. Then we've got Photoshop and you've got computers, and you can either print the pictures on paper in an old-fashioned way. I mean, I don't do that anymore. I think they look better on the screen, but you can. Or with a laser printer, again, a laser. So democratization of the image is complete. I discovered a curious retro twist to this little story. You can now buy, you should look it up on Google, camera lucida apps. for iPhones and iPads. Go back to the 1800s. Now all this physics-based technology, of course it's wonderful, and I could have chosen hundreds of examples. And as I'll get to in a while, it's wonderful not only in the way I've been describing, we'll get there, but as Richard Feynman put it, everything he said was wise and inimitable. Physics is like sex. It has consequences. That's not why you do it. Well, why do we do it? Well, we do it to explain. Now, there are misunderstandings about explanation. A student once, after my quantum mechanics lectures years ago, wrote, now you still have to do it, write your reports, your opinions about what the lecturer told. I enjoyed Professor Berry's lectures, but he didn't explain what use quantum mechanics is. All right, so it explains things, but they would happen anyway. Well, and I can't resist another report. This is just peculiar English. A student who had written a report on a project I supervised, thanks to Professor Berry, who without none of this would have been possible. Anyway, I have talked about what use quantum mechanics is, but that remark, but they would happen anyway, raises very deep questions about the relation between the world and our explanations of the world. Well, I sent it to our Bristol philosophy department. That's their job to think about such things. Now, sometimes our explanations can seem very remote and related only distantly and mysteriously to the phenomena which they are explaining and addressing. Now, I especially like the beginning of a long poem by Wallace Stevens called The Old Guitarist, inspired by Picasso's painting, The Old Guitarist. Now, it wasn't intended, this poem, as a tongue-in-cheek manifesto for theoretical physics, but it could be, actually. They said, you had a blue guitar. You do not play things as they are. The man replied, things as they are changed upon the blue guitar. Now, related to this is another misunderstanding. And it's associated with the fact that we can have a fundamental theory of some particular phenomenon, or even a theory of everything. You know, string theory is a current front runner. But the conceptual distance is of the fundamental is so great from the phenomenon that you actually can't explain it directly. It's a subtle thing, this, but the novelist Ian McEwan made the point very cleverly that a theory of everything might be powerless to explain any particular. You know, there are lots of examples. For example, you know that spacecraft going to the moon obeys quantum mechanics, but you never start by solving the Schrödinger equation to get the trajectory. It's a very subtle thing. But he made the point in a different way. He had this novel, Solar, and he describes a badly behaved string theorist whose wife catches him in a compromising situation with another woman. And he says, "Don't worry, my dear, I can explain everything." I sent that to my philosophers as well. They spent days discussing it. It raises very deep questions about how physics at a higher level of generality can include other theories, usually older ones, as special cases, and which are actually more suited to explain particular phenomena. It's what philosophers call the problem of reduction. I have a great deal to say about that, but not this lecture. There is something familiar, actually, in politics. You know, political people who have an ideology based on a love of humanity as a whole, humanity in general, but in their private lives are incapable of interacting decently with any particular human individual being. It's the same phenomenon. Isaac Newton was very well aware of the point that science proceeds little by little, never trying to explain the universe in its entirety in one go. He wrote this: "To explain all nature is too difficult a task for any one man or even any one age. 'Tis better to do a little with certainty and leave the rest for others that come after than to explain all things by conjecture without being sure of anything." Good. Well, we do explain, and here's an example, not from my own research, example that I really like. Ask this question: Why is gold golden? Okay, it's a question about the quantum physics of condensed matter. The colour, it's a sort of yellow plus shiny, is the light that's reflected on the surface, so it's the light that's not absorbed. Okay, so if you want to understand this, you have to understand the interactions of the light with matter, with the electrons in the matter, actually the electrons in the crystal structure of gold, the material, and see which of that light is absorbed. Then you'll know what's reflected and you'll get the colour gold. Well, to do this, you need to solve the Schrödinger equation. It's quantum physics, of course. It wasn't easy, and it wasn't done until the 1990s. You've got to solve the Schrödinger equation for the interaction of the electrons in the gold with light coming in. It's a heavy computational task. You can't do it on the back of an envelope. Roughly, it involves a particular level in the gold atom, but it's modified by the fact that you've got gold in a lattice. It's roughly the 4D to the 5S transition. And the calculation, when you do it, of course, did predict the colour, and the colour it predicted was silver. Well, it was soon understood what was wrong. What was wrong was this: gold is heavy, and its electrons move fast, comparably with the speed of light. So you've got to include relativity. Now, the relevant quantum mechanics, based on, oops, what am I doing? Oh, help, this appears to have broken. I'll just have to, let me just hope this works, just a second. Let me go the right way around. Let me see. Just a second. Nothing is fatal. There we are, good. The relevant modification of quantum mechanics was the Dirac equation, Paul Dirac. Good, it works. Dirac, probably the greatest intellect, certainly, that my city, Bristol, ever produced. I walked past his house very often where he was born. And when you do that, you get the right colour, you get gold. And that's because the relativity shifts the transition from the ultraviolet, where it was before, that transition, ultraviolet, so the light that's absorbed is invisible, all of it's reflected, and that gives you the silver, essentially sort of whitish plus a shiny. But it shifts into the blue, so the blue is absorbed and all the rest is sort of yellowish, goldish, and that's where the gold, roughly, that's where it comes from. So it's interesting to understand this colour of gold, a key aspect of the metal that's fascinated and beguiled human beings for thousands of years. You need relativity. Gold is relativistic silver. You need the two great physics achievements of the 20th century. You need quantum mechanics of the small and relativity of the fast. It's a very remarkable thing. Now, I learned another example recently. Just a couple of years ago, a paper was published. At last, people were able, quantum chemists, to do the quantum physics of the lead-acid battery. Now, it turns out that, again, lead is heavy, and 80% of the voltage in a lead-acid battery comes from relativity. That's why a tin-acid battery wouldn't be nearly as good. The tin is light, it's in the same column periodic table. So you should think of this. You couldn't start your car with a lead-acid battery if it weren't for relativity. Very remarkable. That's the point these authors make in their paper, just published a couple of years ago. It's very even when you're not driving at relativistic speeds, you're just sitting there and starting your car wouldn't work if you didn't have relativity. Very remarkable thing. Now, I want to change gear. I've talked about some examples of technology that wouldn't have been invented without physics, CD player, or chemistry, photography. And everybody understands this principle. I mean, maybe not everybody really appreciates the democratisation I talk about, but still people know that technology leads to science. The science leads to, excuse me. And we emphasise to politicians how much how any investment in science is likely to generate enormously disproportionate rewards, like Leon Lederman with his 37.9%, not at in predictable ways and not at predictable times, of course, we have to say that. But what we don't usually emphasize to them, although we all know it, is the opposite process. How new technology generates new science. Now, or even new art. In a wonderful book, Philip Ball, the science writer, who was one of our PhD students from years ago, book Bright Earth, beautiful book, he explores in detail how over several millennia, every development in fabric dyeing or paint technology was immediately adopted by painters eager to exploit new sources of colour or new ways to get colour onto surfaces. A fundamental influence of the development of visual art, which is usually completely ignored by historians of art who aren't technical people. Now, David Hockney has developed a new kind of painting on his iPad. It's beautiful. Really, one of you Google David Hockney on an iPad, you'll see wonderful things that he does. Artists grab the latest technology. Now, all scientists use the latest technology, but we don't explicitly comment on it. And my own research as a theoretical physicist has been transformed by the quantum technologies of computers, lasers, digital photography. And I'm going to give a couple of examples, little vignettes from my research over many years, not my main parts of my research, but certain things. I want to talk about Oriental magic mirrors. These were originated in China 2,000 years ago in the Han Dynasty. They're cast bronze with a polished front surface. That's the mirror, and you see images there. My daughter and some trees there. On the back is a deep relief pattern. This one is signs of the zodiac. Now they're made for tourist Christian images or pictures of Confucius. There are many different styles, but that's what they're deep cast relief on the back. Now the magic comes, why they're called magic mirrors, when instead of looking into the mirror, there's the mirror with its front and back, you shine a light on it, the sun for example, you go out in the sun, and then you direct the reflection onto a wall for example. And you look at this bright patch of light reflected on the screen. So you expect to see a bright patch, and you do. But unexpectedly, you see in that bright patch the pattern that's on the back. That's a photograph, the one that I have. It's as though the mirror is transparent. Well, of course it isn't. It's as though the light is penetrating it. Of course it doesn't, and reflects from the back. That's why people call these things magic mirrors. Now, of course, as I say, it's not transparent. And after a century of confusion, when these mirrors were introduced into the West in the 19th century, it became clear that during the casting and polishing, the pattern on the back is somehow weakly reproduced on the front. A bit like greatly exaggerated there. Not deliberately, this I think wasn't a designed-in feature, but by the release of elastic stresses, and in a way that's actually still not totally understood, but it happens. But this didn't explain the optics. How can such a small pattern, too small to be seen by eye, when you look at this mirror, it looks like a perfectly smooth, ordinary mirror. How can that produce this rather striking image? And actually, it's not an image in the usual sense, because you don't have to focus it. It's almost independent of the distance of the mirror from the surface that the screen that you're shining it onto. So it's not like an image focused in the usual way. Well, the answer came from a theoretical analysis, which I won't go into now, but it revealed a scarcely explored regime of old-fashioned ray optics, in which the curvatures of the surface produce the images of the produce the images in a very particular mathematical way. It's a kind of concentration of the light, but too weak to produce focusing, a kind of prefocal brightening. And the theory made a specific prediction. The curvature is the slope of the slope, and for mathematical types, it's very exactly the Laplacian of the surface height. It's absolutely precisely well defined. That's the intensity that you would see. Now, there's a very specific projection from curvature of curvature. You see, these objects consist of sharp relief, sharp steps, And the curvature of a step like that, you imagine it's slightly smoothed away, which it will be on the front. The curvature is a function which has a bright line on one side and a dark line on the other. And actually, you do see that. You see bright and dark on every side. And if you zoom in, that's a simulation based on the theory, and you see these bright lines on every discontinuity. But it's bright on the low side and dark on the high side. That's a very specific prediction. And if you take one of these pictures and you magnify one of these edges and then you smooth it, you see indeed it's got a bright side and a dark side. And from that you can scan it, and then you can actually calculate, you can measure what the relief of the surface is. It's only a few hundred nanometers, it's about the wavelength of red light, so that's why you can't resolve it, but it still has the effect. Now, you see, to do that, you need a digital camera. You take the picture, and you've got the file, and you feed it into a computer, another quantum machine, okay, and you clean it up using Mathematica or some other software. Now, if I were to have done this research 2 decades before, I actually did it, which was about 10 years ago. Before that, I would have needed image capturing equipment and image processing software costing tens of thousands of pounds. 4 decades before, I think it would have been so laborious that people wouldn't have even tried. So with ordinary commercial digital cameras, there's a little digital camera, and standard software on an ordinary laptop, theorists like me can be liberated to do research of this type ourselves. And it's no exaggeration to say that quantum technology enabled the solution of a little physics conundrum which was several thousand years old. Okay, good. By the way, this optics is useful, and there's a few papers about it. It's a lensless way of testing surfaces, because what we do in the semiconductor industry, one way of seeing, quite literally seeing, if a semiconductor surface is flat, is you shine the light on, see you want to be free from scratches and so on, and look at the light reflected on the screen. And it's interesting that it wasn't done for a long time. In the Japanese semiconductor industry, there are papers, it's called Makkyo imaging. Makkyo means wonder mirror, it's their name for this thing. Here's a very different example. In quantum physics, microscopic objects are represented by waves. You know this. And the strength of the wave at any place gives a probability of recording a particle at that place. You know this. Now, as I said, this fundamental aspect of the world was anticipated by Einstein and first expressed by Max Born. It seemed very mysterious, of course, to people who aren't a wave of probability. Actually, everyone's familiar with the wave of probability. Think of a crime wave. That's a wave of probability. It doesn't obey the same rules as quantum physics, but it's a wave. It passes across a city, giving the probability that unfortunate events will occur, but it won't tell you where they occur. Okay? So everyone is familiar with the wave of probability. But sometimes these quantum waves start out concentrated, and they look a bit like classical particles. And they travel in ways reminiscent of particles in Newtonian mechanics, wave packets. And experimentally, you can generate them by zapping electrons in an atom with a laser into very high energy levels. They're called very far out. They're called planetary atoms, very, very big Rydberg states. And these electron wave packets go round and round a few times. But there's a difference from the electrons of a planet around the sun. The difference is this, that as the packet moves around, it spreads. And soon it fills the entire orbit in a narrow ring of probability. Well, about 20 years ago it was realized, again by theoretical analysis of quantum equations, that there's a more surprising difference. After a long time, a very long time, this ring of probability reconcentrates, and you get back the original wave packet, which then spreads and the whole thing happens again. These are long times, quantumly long times. Planck's constant is in the denominator of the formula. And these are called quantum revivals. They occur at multiples, and they've been seen in experiments. Now, quantum revival equations look complicated. And they are complicated. But with computers, again, I keep saying quantum physics machines, we can bring quantum mathematics to life as pictures. Now, this is not always appreciated. I want to talk a bit about pictures. In a few weeks, I'll be one of the judges of a science art competition in Bristol, where people have pictures illustrated. There's a cliche: a picture is worth 1,000 words. But despite that, an equation is a more economical representation, because an equation summarizes infinitely many pictures. But economy and worth are not the same thing. And with the extreme compactness of equations, there comes a loss of immediate understanding and communication, which pictures can remedy. Now, not every scientist has a visual imagination. Many do, but some very good scientists don't. The abrasive but much loved Wolfgang Pauli, he was called the conscience of physics, was very skeptical in the early days of quantum mechanics when Kramers produced pictures illustrating electron waves inside atoms. You now see these regularly in your quantum physics courses. Our good friend Kramers and his coloured picture books. Children, they like pictures. The desire of children for visualizability is reasonable and healthy, but such a desire in physics can never be an argument for maintaining a particular system of concepts. Well, he's right. A picture isn't an explanation, nor does it compel a particular system of concepts, as Pauli said. But it does help us discover phenomena and test explanations. I'm going to illustrate these quantum realms, not with atoms, but with something much simpler. The simpler situation of quantum particles bouncing backwards and forwards between walls in one dimension. It's what people call a particle in a box quantum mechanically, but looked at not in the usual way. Okay, so here's a classical particle, there it is, and here are the walls, left and right, and time is up, so this is space-time. And you know what the classical particle does: it moves and it bounces and it moves and it bounces. That's all it does. Okay. Now, in quantum mechanics, let's have a look at the early stages of this process. A quantum particle. Now, what's it doing? You see, this is at the beginning. It's only 1/20th of this very long time and everything comes back. And what you see is it bounces and interferes with itself. It's a wave, and then but it spreads, and quite soon it will spread to cover the whole space between the walls of the box. But then, as I told you, no, I didn't tell you. Sorry, there's a further subtlety from the mathematics. At fractional multiples of this revival time, say P over Q, 3 over 7, let's say, you get Q copies of the initial wave packet which interfere with each other in a complicated way. Well, a half is 1 over 2, so it's 2 of each. So here's between 9/20ths and 1/2. And here you see what look like two particles. They're not. There's nonsense, people say. People talk about quantum particles being in two places at once. It's not true. The probability of finding a particle is divided into two. If somebody knows that I randomly and equally divide my time between my home and my office, and they want to know the probability of finding me there, they don't think I'm split into two. They know the probability of finding me is split into. Well, so it is in quantum physics, although the rules for calculating are, of course, different. Well, here we are. So this is intermediate. But you see these two probability packets approaching. But the true value of representing this pictorially comes when you look at the complete picture, showing all the time from 0 up to the first revival time. It's this. It's a quantum carpet woven by extreme interference. Now at the bottom, you can see what I showed you at the beginning. This is this little beginning of bouncing, and it comes back again here. But there's all this richness inside. This is what happens in the middle. And you get these curious diagonal lines. You won't anticipate it. You only see them when you do this calculation. And once we saw it, then we can understand it using the mathematics. But we would never have guessed that there are these diagonal lanes, and there's a much richer structure. Not all of this has been seen experimentally, but it must be there. Now, related to this is another example of my underlying theme of connections. You see, we theoretical physicists are never more delighted than when something that we do in one area turns out to be related to what sounds like a completely different area of science. The physicists who studied quantum revivals in the 1990s didn't realize that the phenomenon is mathematically identical to something discovered by the same Henry Fox Talbot who made photography in 1836. It's called the Talbot effect. He was a very clever guy, Talbot. He invented the polarizing microscope. He translated Assyrian inscriptions in the way that Young and Champollion had translated Egyptian hieroglyphics. And he owned a village and was a member of parliament. I mean, you can visit the Talbot Museum. It's near where I live. It's near Bristol. It's in Laycock. Very beautiful sort of chocolate box village for American tourists, but it's very beautiful. And Laycock Abbey now has adjoining it a reasonably quite good museum of photography. Anyway, he was experimenting with light transmitted through a fine grid, diffraction grating, we call it now. Umbrella material, net curtains, you know this. And when you look at a distant light, you see a pattern of bright images, and you know this is the basis of X-ray crystallography, the whole structure of matter, probed in biology, in biochemistry, probed by by X-ray diffraction. That's to do with the far field. But it turns out that if you look at the relatively near field in this way, you look at the screen with the light shining on it with a magnifying glass, you can see the lines if they're not too narrow. Fraction of a millimetre is fine. As you move away, it blurs out. But after a certain distance, it comes back into focus again, and again, and again. And this is the Talbot effect. And Talbot guessed that these repetitions had something to do with the then recently discovered phenomenon of interference, and it was a few decades later when that was confirmed, and 100 years later when the full theory was given. But it's exactly the same. The Talbot effect in distance, repetitions, is analogous, because of the mathematics, to the quantum revivals in time. The time-dependent Schrödinger equation in time is like the space-dependent wave equation in a particular class of cases, with distance replacing time. It's a well-known analogy. Actually, this involves yet another connection. It was the first application in physics of abstract mathematics, something called Gauss sums, invented by Gauss in the early 1800s. And I had long wondered. You see, we come to realize that any deep mathematics will eventually find some application in physics. It didn't already originate in physics. Some does, some doesn't. And I often wondered about these Gauss sums, which I loved for a long, long time, where the physics was in them. And now I realize that it's in these quantum revivals and Talbot effect, if you could consider these phenomena in detail and accurately. And all these fine structures are understandable in that way. I want to briefly, before I get to my last example, I want to briefly illustrate this point, that the same mathematics can describe very different physics, with a different example that has a very personal resonance with me. Here's Max Born's thesis in 1906. I found this because Max Born's son is still alive. He's in his 90s. He's a wonderful man. He's a scientist himself. He was a physiologist. And I met him, and it made me think about Max Born. This is his thesis. And it's to do with the, it's to do with the bending of elastic wires. It's the stability of bent elastic. It's a graph that comes in that theory. Now here's a picture from my own PhD thesis, which is more than half a century later, 60 years later nearly, and it's a completely different subject. It's the diffraction of light by sound, and here's my picture. Now you see it's actually the same mathematics, it's the same set of mathematical functions, and I won't make any comment except that the mathematics common to these pictures was developed in the 19th century as a way of calculating the perimeters of ellipses and elliptic integrals, so that's just something that illustrates the wonderful, there's a physical reason why these are similar, although the physics seems completely different, the wonderful applicability of mathematics in many different ways. My last example, okay, comes now. pretty well everything that I and my fellow physicists do involves computers and technology. Of course it does. Astronomy, the CCD camera, whatever. But give me one more example. I've been exploring a cluster of connections over the last few decades between quantum mechanics, chaos, and prime numbers. Now these primes, you know what they are, numbers that can be divided only by themselves in one, exhibit an exquisite combination of randomness and irregularity. And we know their average density, we know they get sparser as you go up, but we know there are infinitely many of them. It sounds abstract. You can't predict individual primes when you get very high. There's no simple rule, you just have to calculate whether it's prime or not, and that could take a long time. Sounds abstract, but you probably know every time you make a transaction, financial transaction, the encryption uses the difficulty of decomposing a very large number into its prime factors. But there is structure in the way that the primes scatter about their average. And if you represent the fluctuations as a graph, you find it can be decomposed into regular oscillations, just like a musical sound can be decomposed into its harmonies. This was understood by Riemann in the mid-19th century, and people marvel at it. Here's what the contemporary mathematician Enrico Bombieri said. To me, that the distribution of prime numbers can be so accurately represented in the harmonic analysis is absolutely amazing and incredibly beautiful. It tells of an arcane music and a secret harmony composed by the prime numbers. Now there's more, which is why I as a physicist am interested in this. It turns out that the frequencies, the harmonies in the music of the primes are mathematically similar to the energy levels of a quantum particle whose dynamics would, if it were classical, be chaotic. At the heart of quantum chaos is this connection with the primes. Now these connections are very tantalizing, and since we first began to understand them a while ago, they've been the subject of great attention by mathematicians as well as physicists like me pretending to do mathematics. Again using computers and whatever to get pictures in algebra that would have been impossible before. But it occurred to me that nobody has explored this music of the primes acoustically. You can use the expression music of the primes. What about hearing it? Well, I don't have time to describe all the different ways of rendering music as mathematics as sound. I've started to do it recently. Different from sonification that people do, for example, my colleagues with the atomic force microscope sometimes convert the movement of the tip into sound. You can, astrophysicists listen to pulsars with sound, and hear these little glitches. In genomics, there's also sonification of some of the complicated patterns that of DNA, of the genome, errors. But mathematics itself, and at the moment it's more fun than useful. But here are some graphs of fluctuations of the primes. It's a function made from the primes. I don't want to go into details. And if you zoom out, you see what looks like randomness. And it has a kind of fractal structure. And, well, I'm going to play the music. This is the worst sound you've ever heard. There'll be something better later, so allow me this. It looks like noise. It sounds like noise, it is. Now, you can understand why, I don't want to go into it. But if you do something different, if you play the music of the harmonies themselves, this is a mathematical function called, well, it's not happening, called Riemann's Zeta function, never mind the details, it's a function, there it looks, and there you're looking out. It looks noisy but not the same. This is the music of the prime. It's like playing the Fourier transform of something. It's not quite that, but it's related. Then it's a siren, I've got the Siren Song. Here it is. Of course you have to compress it to be within the audible range. of it, you have to compress it more. And then you get the banshee scream of a witch. There's a lot more of this. I don't want to go into it, but there's something called random matrix theory. And there are different types of random matrix, have different structures in their eigenvalue spectra, and you can feel these differences if you render them in suitable ways. You can either play them directly or as phase modulations of carrier waves. It's a whole story, it's a whole lecture which I won't give you. However, if you want to understand why that sounds like what you've just heard, there involves a great deal of mathematics, some of which rescued from Riemann's famously untidy notebooks by somebody 60 years after he died. There's a formula which he invented. Here's his untidy notebook. He did everything that we tell students not to do. He calculates something, then suddenly you'll see the cube root of 2, calculating the 38 decimal places scribbled across. Anyway, hidden in there was a wonderful formula which, if you analyse it in detail, involves a great deal of mathematics. That's very recent work, and you need computers and computer algebra to do it. That's the 20th term of a series, never mind. And that's still being explored. Now, connections. That's been the theme of this talk. And it's trivial when you say it. I mean, you all know physics leads to technology, often after long times and in unexpected ways. And you all know that we do physics not just to apply it, but also to understand things, to explain things. And we also know that new technology leads to new science, and I've given examples of that. But perhaps the examples weren't altogether familiar to you. Thank you. Thank you. Yes, thank you.
Any questions?
I'll tell you a fundamental thing. There are no stupid questions. Or statements.
I've got a question. So, your thesis title, what does it mean by diffraction of light by ultrasound?
Oh, okay. Waves can interact with other waves. So if you have a liquid which has got a sound wave in it, ultrasound, the density is varying periodically. Therefore, the refractive index is varying periodically. And if you shine light in, that periodic refractive is a diffraction grating. So that's an example. That's where the wave that's diffracting is sound and the wave that's being diffracted is light. Another example, much studied recently, if you take two beams of light, and they interfere with each other, they form a periodic pattern of intensity, and if you shine into that crystal of light atoms are quantum waves, the quantum waves are diffracted by interaction with the light, and again you get the diffraction grating pattern beyond. There are many, many examples. Any wave pretty well can diffract any other kind of wave, and that diffraction of light by sound was an old example. There was, in the 1930s, an idea of using that for a system of television. It was never used, never very practical, but it did work. It's called the Scophony system, because by modulating that sound wave, you modulate the light that comes out by diffraction, and if that light that comes out could be a picture. And so if you encode the picture into the sound wave, which you could do, and now you could do it more easily, then that would be a system of producing pictures, but it isn't what we use now, and it never was. But so that was an example. But there are many. Free electron lasers involve similar mathematics. So the kind of mathematics that I did to describe that one phenomenon in the 1960s now applies to lots of others. It's another example of this mathematics appearing in lots of different places. But essentially, the mathematics of a wave being diffracted by another wave is pretty much the same, irrespective of the physical nature of the waves that are diffracted. There are little differences, but not much. So that's what it is.
It's really cool.
Yeah.
Anyone?
Yes.
Do you think that this whole idea of connections and being able to use the same mathematics in lots of different situations is something that we should be explaining better in kind of like secondary school and the like?
Oh yes, everything, of course, yes. Indeed. Okay. Look, if you have a parabola, it has a maximum, or upside down, it has a minimum. You know, I'm talking at elementary levels, so many phenomena depend on minimum energy of something, on stability of structures and so on. And that's something you can explain with care at quite elementary levels. And that's mathematics, a minimum of a curve. It's just kind of simple thing. It's so familiar we hardly think of it as mathematics, but it is. Well, I do, yes, I do think that would be something worth explaining at every level with examples that people at that level are able to understand.
Will there come a point where everything we discover in physics will either be too small in size or at too high energy scales, like unification of forces, to be ever useful for technology?
Don't see a reason. I mean, you know, when the vast energies inside the nucleus were discovered, Rutherford said that it's pure fantasy to think that those very high energy will ever be useful for anything or will ever can be achieved in any practical application. Well, we've got bombs and we've got nuclear power stations and we've got nuclear radiography and you've got annihilation PET scans every time you take an image of something in the brain. Using that technology, so no, I don't see any particular reason. Of course, we as a species may have a finite lifetime, and when we cease to exist or annihilate ourselves, there'll be, up to that time, a largest energy that we've actually dealt with to that point. But you know, while we continue, I see no reason for there to be any limit in either direction. You know, I mean, history would not encourage that that believing in that restriction. We don't know, of course, but I see no reason why. Sorry, excuse me, yes.
Sorry, it might be a bit irrelevant to today's lecture, but it's actually about levitating a frog.
Oh yes, no, very good. I've almost forgotten, but...
Does it actually do any physical harm to the organism?
No.
Or, I'm not from Greenpeace.
Good question. Very good question. I mean, the story was, I can tell this story. I'd been fascinated by a physical toy, which is another lecture which you're not getting, which is a spinning top that has a magnet and it levitates above a surface, apparently violating a law of physics that says that shouldn't be stable. Of course, a magnet will repel a magnet, but if you just try to put a magnet above another one, you turn over and fall down. So this is a toy. It's quite a complicated piece of dynamics which I had worked out. And then I was giving lectures, and I used to carry this toy with me, and people would see this levitation. And then someone said, you know, there's a guy in Holland who's levitated a frog. I said, no, I don't know. Those sound very different. But when I looked at what he'd done, and then I got in touch with Andre Geim, who later got the real Nobel Prize for graphene, okay, but him, it turned out that he'd done this experiment. He had a very strong magnetic field in the solenoid. In fact, for experiments on solid-state magnetism, nothing to do with frogs, but he had this very strong field. In fact, the electromagnets were so strong that they used 6% of the electricity supply of the town in Holland, Nijmegen, where he was working. And so he could only do these experiments at times when people weren't cooking their dinners and so on, whatever. And then so he thought, let me try to see if this could remain. Diamagnetism would repel. And he found that he could make these little water. Almost most things are weakly diamagnetic. Water. Living things are mostly water. He tried rose petals, drops of water, beautiful. He thought, why don't I try something living, this little frog? And it turned out that he did make it levitate, but he couldn't understand why the conditions that he had to apply were so delicate. And then when I got to know him, I realized that the theory was very similar, because instead of a spinning magnet, you've got the electrons inside the atom producing diamagnet. It doesn't matter, it's a similar piece of physics. So I did the theory of his experiment. The frog seemed perfectly unharmed. Not very happy, because it's an unfamiliar thing to be levitated. people, they followed it rather, when this became widely known, this phenomenon, briefly in the 1990s, it was on all the media. And we got wonderful letters from, there was one letter from a leader of a religious cult who said, could I levitate in front of my congregation? Do I have to be naked? And he says, we are very rich, we have a lot of money. To prove it, I enclose a £5 note. Which he did. Well, of course you could, actually, but the problem is that what you need is not just a strong vector, it's a product of the field and the gradient of the field. It's the gradient of the field squared. It needs to be over a very wide range, and nobody can produce these large fields about 4 times, the field for the frog, they're about 4 times bigger than in an MRI scan, so that you don't feel. So it wasn't hard. But to have it over a large volume, to levitate a person, we can't achieve yet. It would be very interesting, and I've written about this on my homepage, because it would be like being in space, but not quite the same, because the diamagnetism of different parts of you is different. So the levitation wouldn't be quite uniform. So, for example, if the diamagnetic susceptibility of your flesh is greater than your bones, you would be, so to speak, hanging by your flesh and your bones would hang. Nobody can imagine what that would feel like. I imagine a very expensive Californian type of facelift. I just can't imagine it. And I would love to be the first human levitatee, but we're nowhere near testing it yet. So we had all kinds of curious, interesting letters that came after that. But the frog seemed unharmed. And it was a little frog, by the way. I mean, this was only about that big, so the frog was tiny. Yeah. You know, about a centimetre or 2 across.
Can we have one more question? No? Well, I guess if you have any more questions, you can ask the speaker during the wine and cheese session.
Oh, you never told us wine and cheese. Thank you. Yeah, good.